Good day everybody, welcome to this new video. In this video we're going to solve a problem by the name of Take 2. So in this problem there's a galaxy receding from us. So when starting from the same shell, its Lyman and Balmer spectrums are 1.138 and 7.22 micrometers respectively. What is the distance modulus between us and this galaxy? And we are also given two constants, this RH meaning the Rydberg constant used for finding the wavelengths of spectrums usually, and the Hubble's constant used for knowing how fast things recede from us based on their distance. So basically, because they're receding away from us, they have spectrums that are elongated, or what we call redshifted, which is why you see very long spectrums here as the Lyman and Balmer. You really don't see wavelengths this long, especially Lyman and Balmer, because those are supposed to be visible to us, but these are outside of our visible range. So what should we do? Well, we should first express their rest wavelengths. So here, you know the expression of finding the wavelength of a certain spectrum right here. So we just have to put it all to the power of -1, like this one, and we can find the initial wavelength. Now, because the initial shell, or Ni, is the same, we can just assume it as x, and we can work for the different spectrums now. For instance, for Lyman, NF is equal to 1, so we just substitute it, and we do the rest of the algebra, and we find here this one. And for Balmer, because NF is equal to 2, we substitute it as well, and we do the rest of the algebra, and we get this equation to express its rest wavelength. Now, because those wavelengths come from the same source, they must also be of the same distance and have the same redshift. Okay, we can express this mathematically. Now, why is this important? Well, we see right here. We've already expressed the rest wavelengths and their accentuated wavelengths, or their redshifted wavelengths, lambda accent over here. They are already given to the problems by the problem. So why is this important? Well, so we can now mathematically compare the things that we already found out earlier. So we substitute in the values for their initial wavelengths here. Don't worry about the lambda accent or the redshifted wavelength. We'll just do it in the end, such that we can just manage all the variables more easily. Now we can just multiply each side by 1 over RH, and these algebraic expressions, just cross multiply them, and we get this expression right here. One thing we will get is that both sides will consist of -1 over RH, x squared over x squared minus 1 multiplied by 4x squared over x squared minus 4, such that we can just cross that out on both sides, and we can just deal with these lambda accents right here. We can also cross multiply these lambda accents as well to get rid of the many x squared over here, x squareds over here, and we end up with this equation. We can then cross multiply again in order to be able to separate the side with the x squared on the left and the side without the x squared on the right. And from there, you can just solve for x. You can just divide this by this and then square it, and we'll get x is equal to 3.02. We assume this 0.02 as a rounding mistake because x has to be a whole positive number. So we just assume this as a rounding mistake and we round it down to 3. It's up to that. When we get x, we can now get the initial wavelength of these. So the initial wavelength for the Lyman is this, and for the Balmer is this. And the redshifted wavelength is this, such that we can just find the redshift right here. For the Lyman, it's 10.091, and for the Balmer, it's 10.001. So rather close there. Let's assume they're rounding errors, and because of that, we can just approximate z is equal to 10.046. Why is 10.046? Because these are the averages of these two values. So yeah, they're also the median of these two values because only two values. Because of this redshift, we find the redshift, we can find the distance. How is that? Well, we know that the z is greater than 0.1, such that the redshift is so big, the velocity of the galaxy isn't of the galaxy itself, rather from more of the expanding universe. So it's relativistic. And then we can just put it in the equation for relativistic redshift. Z is equal to square root of 1 plus beta minus over 1 minus beta minus 1, where beta is equal to V over C. By finding its V, or its recessional velocity from us, we can then find its distance. So basically we just need to find the V, or the velocity, which is inside beta. Put the 1 to the other side and multiply each side by, and multiply the right hand side by the square root of C over C, or speed of light over speed of light, which will be 1. And then we get this is C plus V, C minus V, the square root of those. So we just square both sides, and we also have to remember in Hubble's law, V is equal to h nil multiplied by the d, which is the recessional velocity of a faraway object is equal to the Hubble's constant, the current Hubble's constant multiplied by the distance to the object, such that we can just cross multiply both sides. And after cross multiplying both sides, we'll just divide them all by everything else except for d, for distance, which we will get 4028.947 megaparsecs. Why megaparsecs? Because that's the unit which we use the Hubble constant in megaparsecs. And C, we just adjust it for kilometers per second. Or we will then have to convert it to make it simpler, 4.029 times 10 to the power of 9 parsecs. And from then, because we know the distance, we can then find the distance modulus, or the difference in their magnitudes because of the distance from an observer 10 parsecs away and us, which will be 43.026 magnitudes. And that's our final answer. Alright, this is all for this video. Hope you enjoyed and you learned something new. Thank you.